So hi everybody, and you're very welcome to Fundamentals of AI. This is the third in a series that we've had on the question of AI, and the aim here is to give you an introduction to this fascinating area, and we will just start by talking about how we will conduct the event. So it starts now at 2 o'clock, should run for less than 3 hours. We'd ask you to please stay on mute during the event. If you have questions, please use the Zoom chat function. We'll have a couple of breaks during the event, and we're also going to video this. As I said, we're going to aim to finish by 5 o'clock today. We are working with ICHEC, which is Ireland's Centre for High-End Computing. Simon Wong, Adam Ralph, and Bruno Voisin. Adam and Bruno work for Simon, and maybe Simon, you might want to say a few words by way of introduction.
Hi everyone. So I'm Simon, and I'm in charge of the education and training program at ICHEC. Adam and Bruno doesn't really work for me. We work in the same team more than anything, but I basically manage kind of ICHEC's training program. And just to give, some of you may not have been at the previous event, just to explain who ICHEC is, Irish Centre for High-End Computing. So we are a national high-performance computing center, and we've been around since 2005. And our primary kind of our primary mandate is to provide what's called, high performance computing service for researchers and scientists from all the Irish universities and third level institutions. And basically what that means is, if you're a researcher who need large amounts of computing resources to run, big simulations, you can apply for time on our machine. And so we typically run one of Ireland's largest high performance computing systems. So the one we have now is a system we call K. And so we continue to provide that access. And apart from providing access to the machine itself, we place a lot of emphasis on providing support, helping users work on these machines, and training. And this is just an example today of one of those activities. As you may know, in the AI, deep learning, machine learning field, people require more and more compute resources these days, and and AI type workloads represent a significant portion of what goes on what people do on a machine. But before you kind of get to that stage, people need to start somewhere. So today is pretty much a more technical insight into how you kind of run your first, deep learning model and what that involves. And Bruno will be in charge for most of the session today. So that's a short and sweet explanation of who ICHEC is, I guess, and why we're here today. So I'll hand over to my colleague Bruno, and Adam is also here. Adam will be mostly on the chat, and if you have any questions, post in the chat. Adam will try and help you in the chat room on Zoom.
Yeah, and just before we hand over to Bruno, I just wanted to mention a couple of things. So firstly, this event today is the third in a series. Fundamentals of AI is today's course. All three are recorded, and I'll make sure everybody on the call will get a copy of all three recordings. The other thing to mention is that after today, we hope that you will be armed with some skills and some tools that will allow you to run your own experiments. Now, we're also going to have a set of regular workshops to help answer your questions. So rather than just fire and forget, what we want to do is help you on your journey. So for those of you on the call who have an interest in this, we will have a workshop next Thursday at 2 o'clock. It's an open door, so either nobody comes through the door or 20 people come through the door. We don't know yet. You will receive a link to this as well. Later in the year, we will be running additional courses, and you'll be able to follow our journey by looking at the website. So I'm not going to hand over to Simon's team, but obviously in the form of Bruno. So Bruno, over to you. I'm going to stop sharing and allow you to begin sharing.
Okay, thank you. So hi everyone, my name is Bruno Voisin. Working as a data scientist at ICHEC. So my background is that when I did my PhD from 1999 to 2002, I was interested in this fancy data mining thing at the time. And I managed to get funded to apply data mining to astronomical catalogs. And one thing leading to another, I ended up doing a postdoc with a computational astrophysics laboratory in NUIG. And after that, found a position at ICHEC where I started doing data analytics, data management, not so much machine learning because it was a bit less in vogue at the time, but because things in science are a bit circular sometimes. A few years later, deep learning came to the forefront, launching this AI revolution, and all of a sudden was thrown back into applying those machine learning models, now called AI models, to try and help out people both in scientific research groups or SMEs or public sector bodies to basically improve some of the data analytics. So that takes us to the session today. So a few of you might have been at the session last week. So last week I presented a high-level overview of a first AI pilot project. And I talked about everything surrounding it, everything around it. The one thing I didn't get into deeply is the actual development of the AI model itself. And this is what today is all about. So today is going to be a very different session. If you were there last week were slides and a high-level overview. Today, I'm going to present through a Jupyter notebook with some content and some Python code, and I'm going to take you through that. So today, I have one main goal, and that goal is to get you, even with no prior knowledge in machine learning, my hope is that at the end of the session, you will come out with some intuitive understanding of how those AI models and neural networks in particular work. That is, how they work, what are the general principles involved, what are the critical parameters that we can configure. And the reason for that is that it is brilliantly simple these days to actually implement an AI model. With the modern frameworks and libraries, you can do that with just a dozen lines of code. And I will show you that in the last part of the talk today. The thing is, if you have no idea what is going on behind the scene, what the library will be doing for you, just so that you don't have to, it's difficult then to know how to use them. That dozen lines of code, it will require a few parameters. And if you don't know what a loss function is, you don't know what the learning rate means, you're not sure what an optimizer is, it is difficult to make informed decisions and to properly explore your data and have an AI model that fits for your problem. So let's get started. So we'll have 3 blocks. So the first block today is going to be from 1 to 4 there. I'm going to cover the fundamental concepts. So they're concepts from machine learning, but they do apply to deep learning by extension, and those fancy neural networks are using all that. Then I'll take you through a little tour of some machine learning problem types and some examples just to expand a bit your horizons, give you ideas of some of the models available. And if you have reasonably small data sets, these might be the ones that will get results for you. Now, if you have bigger volume, you will want to use neural networks, and in particular deep neural networks. So this will be the second block today. After looking at the general machine learning things, we're going to see how those apply to designing neural networks, how those networks are made, how they work, what are the principles involved. We'll have a look at that, and then take a tour of what makes a deep neural network different. It's not just the depth of it and the number of layers. There's a little more to that. And after that, we'll have another break. And then the third block, we'll have a look at putting that into practice. So I will use the Keras framework with TensorFlow as the engine, and I will take you through two examples. One to read handwriting digits, and the other one to classify pictures of dogs and cats from the disk, just so that you see how you could easily put your own images with different classes and train your model on that. And hopefully by then, you will be able to recognize all the familiar terms we talked about before. And I should be able, my aim is to convince you that this code there is not that complicated to get started, even though it relies on a lot of work by brighter people behind the scenes. So today I have this thing there. So if you're not familiar with it, this is Jupyter Notebook. This is a small program that runs from that runs from your command line, or that you can host on the cloud server, and it will run this little interactive web page in which you have cells that you can edit, and you can put written content, or you can put images, or you can put code and actually execute that code. So this is a way to do some interactive programming. So this is the way I'm presenting things today. And I'm not sure whether you received a link to the archive for this content, but if not, anyway, we'll make sure that you get it afterwards. You will get this notebook, you will get all the data that it relies on. So if you can install a Jupyter Notebook in a Python environment with these packages there, you will be able on your machine to have this notebook and to reproduce everything I'm showing today. Basically, if you can launch the notebook and if you can execute this cell without any error, you're free to go. If this cell executes with no error, everything else then should work in the notebook. So let's get going. Machine learning. Machine learning in general, the main idea about it is to fit a model to data. So you have data, which is observations. These observations can be text documents, they can be images, they can be numbers, they can be a row in a spreadsheet. You have those observations. And the thing is, you have lots of those observations and you want to extract something interesting out of it. You want to find a pattern. So what is a pattern? A pattern can be a correlation, a distribution, can be clusters. And what do you mean? What do we mean by interesting? Interesting. This is a bit out of context there. It is really domain related. It means useful. So what is interesting, what kind of patterns will be useful or not, that's going to depend on your specific use case. Now, a lot of tools that you use in your daily life tap heavily in those models. So if you have your reading recommendations based on the books you purchased previously, in-car navigation, typing assistance, automated translation, all of that is using AI models in the background. If you play chess or any board game on your phone to pass times in a waiting room, same thing, you have a little AI model behind that is playing against you. Now, there are more sinister use cases, and even though this is not the topic today, this is something to always keep in mind, and especially today, as today is a good day to talk about it because the EU has drafted their first recommendations for AI model use case classification as to which kind of AI models and problems should be acceptable for research and which ones we should try and avoid. Because those models can do a lot of things, and they can do mass surveillance, they can do targeted propaganda customized to your personality and online content, smart bombs, weaponized drones, you name it. There's an AI behind that can power it. So keep that in mind when you do something, and before doing it, I like this quote from Jurassic Park about scientists doing what they wondering whether they could when they should have been wondering whether they should. Because if we do that stuff without thinking, well, we don't even have dinosaurs. It's just sinister and it doesn't even look cool. So what are we going to do? We have data. That's our observations. And we're going to try to find a mathematical model that matches it, that reproduces the patterns we see in there. So to get started and to see it from one of the simplest possible examples, but all the general principles will reapply, we're going to have a look at linear regression. That is when you have dots on a plot and you try to find a straight line that goes through them. So here, I'm going to make a very silly artificial data set where I'm going to try to predict somebody's weight based on height. So I'm going to write that little code there. So don't mind me. This is just a polynomial evaluation function. If some of you are native Python coders, you're going to hate me because my heart belongs to Perl 5, which these days is completely deprecated. So I had to adopt Python as part of the life cycle of programming languages, but my Python programming style has never been very, very clean or academic. So apologies for the horrible Python. Now, let's go about it. So don't worry too much about the code itself. Here it is. I'm going to create an equation, and I'm going to calculate weight as 1.1 times the height in centimeters minus 100. So that's not realistic. It doesn't matter. This is just for the sake of the exercise there. And I'm going to calculate 100 random weights for people of height between 150 centimeters to 210. So this is my data there. So I have those points. Each point there is a simulated observation of a person. I have the height of the person there on X, and I have the weights there. And my job is to find a line that goes through all of that. So ideally, I want to find something like this. Now, what is a line like that? So in terms of mathematics, that's pretty simple. If I want a straight line in there, I need two things. I need the slope of my line. So that is the angle at which it is drawn. And then I need an intercept, which tells me where my line is crossing the line when X equals 0. So those are the two variables that characterize my line. So the ideal line I'm looking for will have those two values. And those two values actually should be 1.1 and minus 100. That is my ideal slope, and that is my ideal intercept. I know because I cheated. I'm the one who created the data, so I know what is the real mathematical formula behind it. But my model doesn't know that, and I'm going to try to have my model discover those values, or at least approximate them. So I'm going to start with random values. So I'm going to get a random slope and a random intercept. Now they are not so random. I make sure that they are close enough so that the plot looks nice. And once I have these two parameters, then I use that function based on the actual observed heights of my people. I'm trying to calculate their predicted weight according to my model. So this is what you see in red. In red are the predictions, in blue are the real observations. It is obvious that my model is bad. It is consistently underestimating the weight. Now, this is something I can see. How can my model discover that? So the first thing we need to do is, how can the model estimate how good or how bad it is? What we want, we know that our model is not perfect. So there is some degree of error in there. How do we measure that? How do we quantify it before fixing it? So there are multiple ways to calculate errors. You can look at that, error functions. There are plenty of them. Classic one is the mean square error. So this is the one we're going to use today. So the mean square error, this is the notation there. Ultimately, it's pretty simple. If you think of this red dot is there. It predicts a weight of 40 kilograms when it should be predicting, I don't know, 62. So we look at this, the distance there. We take this distance, we square it, and then we add the distance between the next dot and its prediction, and we square that plus the square of the next, and then we divide that by the number of observations. So this is our mean square error. The reason to square the error is that it allows two things. It allows us to consider that a positive or negative error will be treated the same. It doesn't matter whether the error is above or below. In both cases, it's by how much we're off that we care about, not so much where we are over or underestimating. If you do care about making a difference between the two, then the squared error is probably not what you need. And the other reason to square is that it's going to make the error progressively more costly on an exponential curve. So that means that very small errors will be considered pretty much equivalent. But after a point, the further you get, the more costly the error becomes. And after a while, your error will be absolutely humongous if you're too far off. So this there is just a little function that is calculating that. I pass it two things. I pass it the actual weights of the people I'm interested in. I know that because I have it in my data set. And I pass the predictions of my model. And then I use that to calculate the differences, square them, calculate the mean. Nothing too exotic. And this is my loss. So this value there is no unit. It doesn't really matter. What matters is whether it's going up or down. A higher loss means a worse model, because that means there's more error in there. So let's see, out of curiosity, we know that our ideal model is 1.1 and minus 100. So let's give it a try. I generate the predictions for my ideal model. I calculate the loss in the same way. And this is the loss for my ideal model. You will notice that it is incredibly smaller, 34 instead of over 1,000. So that works. This there in green, that's my ideal model. You can see that, of course, it's not perfect because my data is not perfect. People are not perfect. They are a bit random around it, but it does a good job of giving me an estimate. So this is ultimately what we would like our model to converge to. So how do we do that? We're going to minimize our error. We know that a lower error is better. So we want to modify our parameters. We have two parameters defining our line, the slope and the intercept. We can modify them. I can increase the slope. I can reduce the slope. I can leave it like it is. I can do the same with the intercept. And doing these things will increase or decrease my loss, or it will leave it approximately to the same thing. So I'm going to explore those possibilities, and I want to find out which combination, which one I should increase, which one I should decrease, whether I should do the two together or do the opposite for each one. And I will find what is the best possibility, the best way to modify those parameters so that my loss goes down, 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 down until it can't go down anymore. So how we do that? The strategy to actually modify our parameters, this is our optimization strategy. So you will find when you set up an AI model, you will have to choose an optimizer or an optimization strategy. This is what we're talking about. There are multiple strategies doing that, and this is what it's about. It's about, okay, there is a function to calculate the error. This is what we call a loss function. This just tells you how bad your model is. After that, how you use that loss to modify your weight so that the loss is a little less worse. This is your optimization strategy. This is the job of the optimizer. So we're going to look here today at the gradient descent. Very often you will find it abbreviated as SGD in libraries for stochastic gradient descent. So if you see SGD or SGD optimizer, this is what it's about. So we're going to have a look at it because it's simple. It's even very intuitive. Hopefully I will convince you of that. And if you remember your maths before, and if you have studied, in particular, if you remember derivatives, which were telling you whether a function was going up or down, at the time it might have been a bit boring, and you were wondering, who cares about that? What good is it to me? Well, this is what it's good for, at least one of the uses. I'm sure my mathematician colleagues would come up with plenty more examples, but that's the only one I have in mind. So let's find out. Let's find out intuitively. So I'm just going to look at the slope. You remember I have the slope and intercept of my function. I can modify those two, and I want my loss to reduce. So I'm going to forget about the intercept for now. I'm just going to focus on the slope. So my intercept stays as it is, but I'm going to generate plenty of slopes. So I'm going to go from 0.5 to 1.5 in steps of 0.01. So I will have 0.5, 0.51, 0.52, etc., until 1.5. And for each possible slope, I'm going to calculate the loss of my function. What is the loss of all those possible models with different slopes, but with the same intercept? And this is what I'm plotting there. So for all those slopes there, this is what the error looks like. And the red dot is where I am at the moment. My current random model has a slope of 0.81, 82, something like that. And this is my loss. My loss is like this. So you can see there that if we have a smaller slope, smaller value, then our loss will increase. If we have a higher slope, our loss will decrease up to a point, to about there, 1 point. It's not quite 1.1, 1.1 would be here, but closer to 1.05, maybe 1.02. This seems to be the best possible value for the slope. And after that, if we keep increasing the slope, then our loss is continuing to increase. Do you see that plot there? This is what we're looking at. This is what we want the model to understand. So it is obvious to the eye when you look at this plot that do we want to reduce our slope, increase it, or leave it as it is? It is obvious that we want to increase it. It is also obvious that we don't want to increase it too much, because if we do, then will be too high. So how the model is going to do that? Well, this is where those mathematical derivatives are coming. This curve is based on a mathematical function. The mathematical function is the function that draws our line. It is a small equation. Now, in case you haven't studied them, the derivative of a function is another function that you can calculate from that equation. An interesting bit about it is that the value of the derivative of a function is going at a special point. So here at the red point is going to be positive, negative, or equal to 0. And that's incredibly interesting, because if the value of the derivative there is positive, that means that your function is going up. For example, here, the value of the derivative would be positive because the function is going up from left to right. If your value is negative, it means that you're going down. If the value is 0, it means that you're at the point of inflection. And the beauty of it is that these days, we don't have to calculate the derivative ourselves. We have mathematical libraries that are going to do it for us, that are going to estimate that. So the value of the derivative at a point, this is what we call the gradient. This is that value that can be positive if the function is going up, negative if it's going down, 0 if it's flat. This gradient is interesting because this is a way we have to tell the model, for the model to guess whether it should increase or decrease the value. We know that we want the loss to go down, so we want our function to go down. So if our gradient here is negative, our function, then we know that we want to increase our value. We want to go a bit further there to the right. If it is positive, that means that we're going up, and we don't, let's say we're here. If the gradient is positive, we're going in the wrong direction, so we want to come back. So that's going to inform us. And another property of the gradient is that the steeper the slope, the bigger the absolute value of the gradient. So here, the gradient is more negative, is a high negative number. Over here is going to be a small negative number, small positive number, high positive number. So the gradient is not only telling us the shape of our curve, it is also telling us at what point of the slope we are. So we know that if we're on a very steep section, because our loss functions generally are curves like this, we know that here we can adjust our value by a lot. If we have a small gradient, we know that we are near the point of inflection, we are near the optimal place. So we know that when we are here, we want to be careful. We don't want to modify our value too much. We don't want to go too far. So this is the principle of your gradient descent. You have your function. My function here are just 2 parameters, coefficient, the slope and the intercept. I'm going to freeze a parameter, so the intercept. I don't modify anything to the intercept. And then I have the equation for my function with a single parameter. I calculate the gradients for it, that is g. I calculate my gradient where I am. And then I use that gradient to modify my parameter, so in this case, the slope, by the gradient multiplied by LR. This is an extra parameter of the model. This is the learning rate. This is one of those values you will have to give a number to. It's a multiplier of the gradient, so that means that the high learning rate means we're going to go further towards the right. A smaller learning rate means that we're going to take a small steps. So for example, with a small gradient, my next value might be here. And then another step will possibly take me there. Another step will take me there. And as we go, at some point, we'll end up here. Now, if I have a high learning rate, I might have my first step taking me here. And then my next step might take me there. And then with my high learning rate, I will see that I need to decrease, and maybe I will come here. And I'm going to oscillate left, right, left, right. So this is the learning rate issue. A high learning rate will allow you to go down that curve faster. But if you're close to the best point, you're going to do a lot of overcorrections all the time. So don't mind that too much. This is all going to be encoded in your library, but this is how you do this. We do this for the slope of our line, and we know by what is the new slope, adjusted slope, that will result in a better model with a lower loss. Then what do? We also have the intercept parameter. So we're going to freeze the slope to its current value, and then we're going to have a look at what this loss curve looks like for the intercept. We're going to calculate the gradient. We're going to adjust the intercept to reduce the loss. And now we have a new slope and a new intercept that are going to reduce the loss of our model. If we had 50 parameters, it's the same thing. We just adjust each of those 50 parameters in turn one after another by freezing all the others and just varying one of them by calculating its gradient. And that's all there is to it. It's just a lot of repetition of that same thing there. So here, don't mind this too much. This is just my own implementation to calculate the gradient. Just use a trick to estimate them from the curve instead of doing a proper mathematical derivation. So sue me, I'm not a mathematician, so I'm an applied scientist, so I'm going for the applied solution. And then I generate an update model function that is going to update my model based on the gradients by reducing the parameters by the gradients multiplied by the learning rate. So I'm going to demonstrate that in this bit of code there. I'm going to print out my coefficient and print out the loss. This before modifying anything. Then I'm going to calculate my gradients. I'm going to print them. I'm going to adjust my model with my gradients, and this here is my learning rate. And once this is done, I'm going to show the model after the adjustment and the loss after the adjustment. And hopefully the model is better and the loss is lower. So there we go. This is my model coefficients before. This is my loss. These are my gradients. So this is the gradient for the slope. This is the gradient for the intercept. And then after my adjustment, this is my new slope. This is my new intercept. And this is my new loss. And you can see that my new loss is much lower. So mathematically, it checks out. Visually, let's have a look. This is my model before, and this is my model after the adjustment. And you can see visually that the model has gone closer. If I was to repeat the same thing there, that green line would get closer and closer and closer to the middle. And after a while, it will stop improving. The loss will stay pretty much constant. At that point, I might want to stop and just use my model. And I have approximated my data. I've found the line in the middle. So there's a lot of simple but boring work for just tracing a line. But the beauty of it is that here, I'm just using a single parameter there to predict another one. But if there are more, it's not a big deal. I just repeating more of the same, and computers are very good at that. They don't get bored. So let's have a look at it. Here, I'm going to define a third order polynomial. So I have my intercept there, and then the coefficient for the various degrees. So, and I generate random data. So there we go. This is what my data looks like. I create a random model, and there it is. This is a random third order model. So my red line obviously isn't fitting very well. I'm going to apply the exact same code I had before. I'm calculating the gradients for my model. I have my input, my output. I calculate my gradients. I have a learning rate, and I modify. And there we go. This is the first iteration. This green line there is the improved model. Obviously, this is not finished, but if I repeat that, more and more and more, after repeating those steps, I will end up with a green line that will go in there and fit. Simply because here, what I've done is use my gradients to improve this coefficient, then this one, then this one, then this one, each time with only one goal, reduce the loss. And this is going to be a universal constant. This is what all the models are going to do. So we'll come back to that for neural networks in particular, because that will be part of how those networks are trained. Now, before that, we're going to have a talk about overfitting. So we're trying to find the line that goes through our dots, and we want to make it as good as possible. We want our loss to be as low as possible. Now, there is a little risk in there, and it's not exactly clear-cut all the time what is the right thing to do. So we're going to have a look at that visually. Have a look at this data. What would be a good fit there? It's difficult to say. Okay, so let's think. What is the good fit here? Is it a line that goes here? Or would it be a line that goes like that? Some weird function doing this? Or is it just a function there and these are outliers? Or is it a function that increases like that and these two are outliers? Who knows? It's difficult to tell. Now, you may notice the scale there in Y. Now, let's say that the Y values can go from 0 to 1. This is, this is our domain. We know that we are looking at values that are generally between 0 and 1. All of a sudden, if we plot that, sorry, minus 1 and 1. If we plot that between minus 1 and 1, okay, our data doesn't look as weird anymore. And all of a sudden, the straight line theory is no longer so far-fetched, and it looks like potentially the better model. We're probably looking at a straight line model there that would work reasonably well. So just looking at the possibilities of values, the distribution of values, this is already something that we have to keep in mind because it helps us make sense of the data. Now, we want a model that is going to reduce the error. If we look at a straight line there, okay, sorry, this is not very straight, but that's the zoom trace function there. This one is a bit better. Even my straight line there, you can see that it's not perfect. There is some error. What happens if I throw a very fancy, very complicated AI model onto it that is trying to minimize the error? Well, this is what happens. My model has found a mathematical equation that perfectly matches the data, and that results in an error very close, in a loss very close to 0. The loss is minimal. It is even smaller than my red line. But is that a good model? Is that a true representation, a good predictor for my data? I'm not sure. It's difficult to know. So this is a risk when you throw too complex a mathematical model onto data that has a simpler explanation. You run that risk. This is a case of overfitting. We have a model that is trying too hard to match the exact properties of our data. And that results in something that doesn't work out well. It works out well for those blue dots, but if I'm here, I would expect a value there. And in fact, my model is going to give me, instead of 0.5, it's going to give me -1, which is possibly not great. Now, of course, the possibility is that in your data, you may have a dot somewhere there. Is that dot a real observation, or is it an outlier? That's a question mark. If that dot is there, it's going to strongly encourage this model, because the straight line will have a massive error due to this one. So this is no longer about overfitting. This is about outliers. So be careful about the data you use, because it is very easy when you're fitting a model. If you have some degree of bias, if you have some outliers with a clear pattern somewhere, that is going to distort your model, because your model doesn't know that this data is not quite representative. It can't make the difference, and it will try to find something which mathematically fits them. Now, of course, if I was getting more data and I see that my dots are there, well, okay, that's more information. That tells me that this one is very, very likely an outlier. Plus, even if I don't discard this guy there, because it's not necessarily a good thing to discard inconvenient data, depending on the use case. More data, more observations which fit properly means that the error caused by this one on my straight line model will not be as bad, because it will be mitigated by more data. And when I do a mean square error, then it will be reduced. Plus, more data means that in order to overfit, the model will have a lot more work to do. So this part there is also a little demonstrator of the importance of having enough data to work on. The fewer data you have, the easiest it will be for a stupidly complicated model to find a completely weird curve that goes through it and works on paper, but then is completely useless when you try to put it in production. So how are we going to do that? How can we address that when we're training a model? So a way to do this, and this is going to be a constant, whatever AI framework you use, is you're going to split your data, your observations, and your all your observations into training and testing data sets. You're never going to train your model on all your data. You're always going to take a portion of it, say 80%, train your model on that. But then after that, you're going to evaluate your model on that other 20%, which is your testing set, and you're going to evaluate and see how the model fares at predicting these ones. And the beauty of that is that the model will not have seen that 20%. It won't have trained on that. So it is impossible for it to have overfitted these ones. So ultimately, you're looking for a model which does well in training and replicates that accuracy on the testing data. If you have that, this is a great model. If your model is doing perfect on the blue dots, which are your training data, but is doing abysmally bad on the green data, green dots there, which are our testing sets, that means that you have an overfit. So this is a quick schematic there. You have the training error there. Your training error can be low or it can be high. And your testing error, the error on the testing set, can be low and can be high. If your training error is low and your testing error is low, this is a great model. If your training error is low, but your testing error is very high, you have a model that is overfitting. If your training error and your testing error are both high, well, this is underfitting. Basically, your model doesn't work. It didn't find any pattern. And then if for some mad reason, you have a very high training error, but your model works, does wonders on the testing sets, I don't know. I have no idea what you've done. I would say it's probably random luck, and the garbage model that you have trained just happened for some mad reason to perfectly fit the testing sets that you had selected. It's just sheer luck, and it is by no means representative, and you don't want to use that model at all. In fact, send me an email if that happens, because I would love one day to present a real life example of somebody to whom it actually happened. It should. So a quick note on overfitting. The more parameters you have in the model, the easier it will be to overfit. In fact, it's more complicated than that. It's the more parameters you have compared to the size of your training data, the more it's likely to happen. That is, if I have 3 observations and I'm trying to generate a mathematical equation with 200 variables to model my 3 data points, there are so many possibilities that it will be very easy to find a stupid equation that perfectly matches those 3, but it's not going to be representative. We'll talk about that number of parameters later. Now, another thing to keep in mind regarding to over-underfitting, it is that when you're splitting your data between training and testing, there might be a selection effect. That is that the testing data, the 10 or 20% that you have saved for testing, they might just happen out of sheer luck in the random selection process to be very, very close to some of your training data points. And that means that when your model is going to be evaluated on the test data, well, it will score very well because those data points happen to be very, very close to similar examples. There might be more unique data points in there with different properties, but they're just not in your testing data, so it's difficult to know. So k-fold cross-validation is a way, if you ever have that kind of issue, is a way to go around it. That is, instead of splitting your data once and evaluating your trained model on the testing data and calling it a day, what you can do is you split your data into k partitions. So here, 1, 2, 3, 4. We split our data into 4 partitions. And then we're going to train not 1 model, we're going to train 4 models. We're going to train 1 model with this training data and test it on partition 1. Then we're going to train another model on this data and test it on partition 2. Then 1 model trained on this, tested on partition 3, then 1 model on that, trained on partition 4. And then we're going to calculate the mean value of our validation, accuracy, whatever measure we use, and that will give us a realistic idea of how well our model can fit the data, free from selection bias in the testing sample. Again, this is something that frameworks will do for you should you need it. And also, it is not very carbon cost friendly because if you do 10-fold cross-validation, you're training 10 times the number of models, and they are expensive to run on big GPU. So keep that in mind. Don't go overboard depending on the amount of resources you're using. Now, this is it for the key concept behind the machine learning. The next step will be to look at how they apply to neural networks. That will be in the second part. Before that, very briefly, before the pause, I'm going to just discuss a few machine learning problem types and technique examples. So regression, this is a word that you will see all the time. A regression problem is when you try to predict a response variable, often referred to as y, from a number of predictor variables that we refer as x often. It doesn't mean that there's just one variable. X are the predictor variables, so there can be plenty of them. In machine learning context, what you're doing is you're trying to find an equation that uses x, an equation on x, that predicts Y. And linear regression, what we've done just before, is a typical example of that. As opposed to regression, we have classification. Classification is when your data is actually in an arbitrary number of groups or categories, and you want to predict that category. This is different from regression. So let's see here. This is a random set of data that I generate, and I have yellow dots and I have blue dots. And I would like to know, okay, if I have a dot at some XY coordinates, is it yellow or is it blue? This is what I'm looking for. And the issue is that yellow and blue are categorical. They're not exactly a value. So there is no real relationship between that. I could eventually treat it as a regression problem. I try to fit a model where I'm going to say that if I have a negative value, then it's blue, a positive value, then it's Y, then it's yellow. That will sort of work, but does a higher value, what does a higher value mean? Is it more yellow or less yellow? What is the maximum there? I don't know, I'm not too sure. It's a bit complicated. And what if I have three colors? If I have blue, yellow, and green, how do I do that? Do I put an interval in the middle? There is no real relationship. If I have values from -infinity to -100, that's blue, -100 to +100, that's green, and +100 to infinity, that's yellow. I could train a model using that, but does that work? It's a bit weird. There's no real order. Something that is near 100 -100 will, according to my model, be closer to blue and green than yellow. Is that realistic? I don't know. So this is the problem. It is that here we're trying to predict a category. We're trying to predict a number of fixed cases and not a floating value. And this is a response that is said to be categorical. So what do we do? This is where logistic regression comes in. Logistic regression is basically using a regression model and tying up what we call a logistic function at the end of it for the prediction. Our model ultimately is always going to use numbers and predict floating values, but we can use a logistic function to constrain then that result and transform it into a smaller interval that will be meaningful for our problem. So here, for example, what you see in blue, that is the sigmoid function. The sigmoid function is going to take a value between -infinity and +infinity, and will return me something between 0 and 1. And between 0 and 1 is wonderful, because 0, 1 is the range we expect for probability. So it means that all of a sudden we have something that is outputted between 0 and 1. And in the case of that thing there, we can say that what our model is predicting is the probability that a dot is yellow. And we know that when we train, when we use our training data for yellow dots, the probability that we expect the model to find for that dot to be yellow is 1. It is yellow. We want the model to find 1. If it doesn't find 1, then the difference between 1 and that's our error. And for a training dot that is blue, the probability we expect our model to find would be 0. And if it doesn't find 0, again, by how much it doesn't find it, that's our error. And we can calculate our loss, which means we can calculate gradients, which means we can adjust our model and we can converge to a solution. Now that works if we have just 2 possibilities. If we have more than that, that will work too. I'll show you later how we get around that. Okay, so that covers it for the clear basics of machine learning. The final thing is to make the distinction between supervised and unsupervised learning. So pretty much everything I presented until now, this is a typical case of supervised learning, and it is very likely that this is something that you will need. supervised learning is when you're trying to predict something that you can see in your training set. You have a training set with what we call a ground truth, that is something you want to predict. You have historical data that shows you something, and you want to be able to predict it in the future. So whether it is the example where based on height, I want to predict the weight, or whether it is based on properties of a house, you want to predict its price on the market, whether it is from an image, you want to predict whether this is a good part or whether it is a broken part. All of that, this is supervised learning. You train your model by giving it examples where you have your predictors and you have the response variable. You have the two, and your model is going to train to match it, calculate the loss based on the non-response and the predicted response. So this is how it's going to work. You're going to create your model. You're going to train it. And to do that, you need your training set with the input and the output. You're going to refine your model. So this is a big part of it. Refining the model is that in practice, sometimes the first model you throw at it might not work. You're going to fiddle with it. You're going to change the number of layers. You're going to change some of the parameters. You're going to change the learning rate, etc. You're going to experiment. And every time you do that, you're going to evaluate your model to the testing set, find how it works. And once you're happy with that, after you've done that cycle a few times, you're going to use your model for inference. That's it. You can use it to make predictions. And how you put that into your production chain, that depends on your problem. So a few examples of supervised learning techniques, decision trees. I'm going to go very quick on that because that's not terribly relevant for today, but you have it in the slides, should you be interested. It's just to show that there is more than neural networks. So here we have a decision tree tries to predict whether infants will develop a special condition of the spine. So after surgery. And the predictor variables, we have age, number of vertebrae affected, highest vertebrae it was operated on. And based on those values, there's a tree that is constructed automatically, telling us that, okay, we have something, we can see whether the start variable, so the starting vertebrae, is it 9 or more? Yes, no. If no, then yes, the kid is very likely to develop the condition. If it is greater than the 9th vertebrae, then we have another test there. Again, so is it between 9 and 15? And here, what is the age in, I guess, days? And every time the box at the end tells you what is the verdict. So there are extensions of that, but basically these are techniques that work on smaller data samples. Here, the training sample was just 81 cases. So it is interesting, but not for what we are doing today. You have other techniques like super vector needs, which are going to transform your input data and try to find a transform mathematical space where your data can be separated by a hyperplane. Again, I'm not entering into the details, it doesn't matter too much. But the final thing I want to discuss is unsupervised learning. Unsupervised learning is what you do when you're not looking for a direct answer, you're just looking for patterns. And you don't have a specific value that you try to predict. You're just exploring your data, trying to find something in there. And for example, clustering is a typical problem. That is, you have data, you're not searching for something. You have a number of funds, investments, and you say, okay, how do they group up? What are the, can I categorize them into a number of groups that are close to each other, just so that you can analyze then what are the common factors. So a second example. If I give you this data there, and I'm asking you, okay, how many clusters do I have? To the human eye, it is obvious we have 2 clusters. We have one there at the top, and we have one there at the bottom. Now, okay, that's fine. Let's say that this data is about financial transactions, and they can be legitimate. I color them in green, or they can be fraudulent, and I color them in red. So this could be the case. It could be that my fraudulent transactions are there, my legitimates are there, and so my clustering in 2 clusters there, this is great because, hey, that matches. So I run my clustering there, and then I take a look and I realize, hey, look, my clusters work. They actually help me predict what works, what doesn't. But the thing about unsupervised learning is that you'll not necessarily get what you're looking for. You get what the data is showing. And it might not correlate to what you're expecting. So for example, I could have my fraudulent transactions there in yellow and the legitimate ones there in blue. And here, to the human eye, it's going to be obvious that we could trace a line there, and that will be a decent enough predictor to tell us that anything under it should be legitimate, anything above it should be treated as suspicious. But the thing is, if you had run a clustering algorithm, there is no way you would have found that. You would have found one block here, one block there. So this is something to keep in mind. Clustering can do wonders, unsupervised learning can do wonders, but the results should never be overinterpreted. You will always have to be very careful about what they're showing, because that might not match what you had in mind. And so this is an example there of clustering technique, k-means. This is an old classic one that works on small small data sets. You set a number of clusters. This is one of the issues with that technique. You have to define how many clusters you want to find. And then after that, you let the model optimize it. It generates random centroids. And then over time, it's going to adjust them. And there we go. That's the final state there. So I have a centroid here, centroid there. And based on which centroid a dot is closest to, I consolidate in one group or the other. So I'm not going to say much more about that. This is just an example of unsupervised learning. There are actual a lot of more cases of unsupervised learning. Typically, autoencoders are one deep learning technique that is unsupervised and used, for example, for colorizing black and white images. For example, this is, again, unsupervised learning based on generating training networks with an image as the input and the output. And there is some magic going on in the network that allows us afterwards to automatically regenerate the colors. But this is going to be a bit off topic for today. So I spoke a lot for this first block. So I'm going to propose that we take a 10 minutes break so we can meet again at 3:20. And we'll get into the second part. We're going to dive into artificial neural networks. And we're going to see how those concepts we have seen apply directly to NNs and then deep networks. Of course, during the pause, I'm around. So if you have any questions, feel free to give a shout. Thank you. Interesting the question by Roman. So usually when separating the input data between training and testing, as I said, there are functions doing this for you. Okay, Adam is answering.
Yeah, that was only part
And
of my response there. So I was going to say what I forgot you could turn on the microphones. That would have been easier than writing it. But what you want to achieve with the test set is that it's going to be an unbiased representation of any new data that you're going to acquire. So in the case of time series data, usually you want to predict future data. So it makes no sense in that case to randomly split your sample. You would want to split it in terms of, data, in the past, you determine a time that you're going to split the data into training and test, and the training will be the past data and the test set will be the future data, because the new data that's going to come in is going to be future data. So that's why you would do it that way. And also, of course, you keep the kind of time frequency good in both sets. But normally, you would split it kind of randomly, and certainly for the k-fold cross-validation, that's that's what's intended to do.
Hey Adam, yeah. Thank you very much for your answer. Actually, yeah, obviously in the concrete example that you were talking about, the time, obviously it would make sense that it cannot be random, because obviously if it's random, it can be given not the right data, and obviously it wouldn't make any sense. But yeah, I was mainly asking just because it's true that, for example, whenever you can be making a random split and of normal data, not in that concrete example, but of normal data. It's true that maybe in one iteration, so you can get the random split, then you train the model, then you get the prediction, so with one iteration. And it can happen that you can get a prediction, but it may happen that in the next one, for example, it may vary a little bit, and it can also be affected by how it has been randomized. So for example, some of the times I have been already setting the seed on the on the randomizer whenever it was generating the train test split, just to kind of like avoid that was a factor of making the accuracy lower or higher. But yeah, that was why I was seeing now that the k-fold cross actually could also help on those kind of scenarios, obviously.
Yeah. So yeah. If you have to set I would say there's probably something wrong either with the data or the model that you're using. So, if it's dependent, if your model is going to be dependent on what set of data you set aside to be the test set, then I think it probably, when you try and generalize that model, it's not going to work very well. So
Yeah, exactly. I agree with you. Yeah, I was feeling that sometimes it could happen, for example, that not concretely in any model that I was working on, but I could have seen on some people that I was either doing the model with or something, that I could feel that whenever, for example, there is not enough data and it's so easy to overfit and the model to generate patterns, yes. It's very easy that this can happen since, for example, there can be some data that can be much more easier for the model, let's say it like that, and some others that can be more complicated, and that's why this can be a factor. And obviously, if you have a lot of data and then the model can train perfectly, then it usually won't have a problem how you are randomizing the data. But I'm saying, I was just kind of saying, just because it can be very easy to kind of like interpret not in the right way sometimes, based on how you have randomized data, in case that you don't have enough,
Yeah, well, I think, Bruno, you're going to talk about generating kind of artificial data. So if you don't have enough data, then that may also be an option, and does actually work quite well with deep learning models. So either that, or you have to, there are, of course, regularization techniques that you can use to stop overfitting, but I don't think any of them necessarily will prevent overfitting. Will definitely prevent it, but it will kind of, you know, is less likely that your model will overfit. So they're your kind of best options. I mean, typically the examples you see on deep learning, they don't do k-fold validation because, you know, the model can take hours or days to run, and you're not going to want to run it 10 times. So, you know, if it takes a day,
and when you have a very large amount of data, the selection risk, the risk of selection bias is generally lessened if you have a humongous amount of observations to pick from, unless, as in the case of the time series, for example, there is actually a specific pattern in the data that should be guiding the selection. But otherwise, a random selection should work out. It's only on a small data set that you run the risk that specific observation will create very different models. All right. Anyhow, it's time to get going. So welcome to the second part of the chat today. And now that we've talked about some of the general concepts of machine learning that will apply to deep learning, we're going to talk specifically about neural networks. So what are artificial neural networks? So they are pretty old machine learning techniques, which is used originally mostly for supervised learning problems. But as I said, with autoencoders, for example, they can be used for unsupervised techniques. So they're actually pretty versatile. The main thing they have for them is that they can generate very, very complex mathematical equations. If you remember before, I showed examples of data that I was generating manually from polynomials up to a fourth order, but I could have made more complicated stuff. The thing is, real data is more complex than that. It can obey to mathematical functions that have hundreds, thousands of parameters. It can be very complex to model. And sometimes there is not a perfect equation, and even a good enough approximation will be very complex. It won't be a linear function. So the lovely thing about neural networks is that the way they are designed means that they can represent that kind of data, where trying to fit a polynomial will never work, or trying to fit a straight line even worse, or whether you can't naturally split the data subsequent one partition after another, like in the decision tree. Sometimes those simple approaches don't work. They're just too simple, and the data is way more complicated. So ANNs do that. So it's time now for the completely irrelevant picture there. This is a schematic of a neuron in the brain, and this is what artificial neural networks are supposedly based on. So if I remember correctly, my biology, I think the neuron is receiving lots of signals there. And after enough information is received in there, I think it emits something through there and sends a message to the next neurons. And you have lots of them in the brain, and then we can think. Sorry, I'm not a biologist. It's a good thing my wife isn't there, because she is, and she would murder me for that. Gross oversimplification. Anyhow, the idea is that we're going to design artificial neurons that are going to do the same. They're going to get lots of information, and they're going to combine that information to send a signal to other neurons. Then we're going to put plenty of them together. We're going to connect all of them, and hopefully that will work, and we'll have something interesting. That's the idea. So if that works, we'll know, because we'll have created an AI, and it will take over the world, and we won't have to think about it anymore. Now, okay, it's not quite so simple, but that was the original idea, and that's how the idea has grown. So as I was saying, it's a very old thing. It started in the 60s, and people had those wild dreams about artificial intelligence, what those neurons were going to do, and how we're going to replicate the the thinking, but it didn't quite work like that. Thing is, it was incredibly costly computationally. The computers couldn't handle it at the time. And ultimately, people believing in neural networks were pushed into a corner. They were called connectionists, and their friends would pretend they didn't know them. And real machine learning was the rest of the stuff that actually worked and didn't require so much computation to actually do something. Now the tables have turned, of course, and the connectionists are having the last laugh because neural networks have taken over and are doing everything. Now, okay, so let's have the classic diagram that you will see everywhere. If you had any interest in neural networks before, you have seen tons of those diagrams. This is what a neural network ultimately looks like. The number of nodes may vary, but this is the general shape. The way you read that is from left to right. And you have a number of inputs. So these will be your predictor variables, if you remember X. So they are predictor variables. And let's say all the attributes that describe a house. So the number of rooms, the orientation, the superficie, the size of the garden, whatever it is. And we have an output. So let's say the price on the market. And what we're going to do is we're going to take those input values. We're going to multiply them by random weights. So each time you see an arrow, this is weight at the beginning of the network, a random number. So we're going to multiply the number of rooms of the house by a random number. And we're going to add that to the floor surface of the house multiplied by another random number, multiplied by, I don't know, let's say the energy rating of the house from 0 to 5, multiplied by a random number, plus the size of the garden, multiplied by a random number. All of that together, that's the value we have here. Now we're going to do the same thing with other random numbers into there, and into there, and into there, and into there. And then we're going to take all those things, we're going to multiply them by more random values, add them together, and this is our output there. And what we're going to get is absolute garbage at first, but then we'll work on that. So as you can imagine, we could add more layers in there. Instead of going from these blue dots to the output, we could have more blue dots. And instead of having 1, 2, 3, 4, 5 blue dots there, we could have 10 of them, 20. So the more dots, the more layers we make, the more weights there are, the more connections, the more complex the mathematical equation is. And you could, if you gave a name to each arrow there, you could write down the mathematical equation, which is a function of these 4 inputs, and gives that. And the more dots, the more blue dots you have, the more complicated it will be. And it can be absolutely massive. So this is where the power comes from. They can represent lots of things because they have lots of parameters in there. So this there, this is a small graph of a single node. So think of this as a blue node, and these are the inputs. So if it's a blue node here, then the inputs are those green dots. If this is my red dot, if it's my outputs, then those inputs there would be the values coming from the blue. So I have my input values, x1 to xm, and I multiply them by weight. So my weight k1, my weight k2, etc. And I sum all of that together. And then there is a little fancy extra one, which I didn't show on my graphics. This is what we call the bias node. This is a small value. This is an extra node not connected to anything with the value 1. And it is multiplied also by a random weight that we're going to adjust. What is it for? Well, that's the artificial way to represent the intercept of a function. I multiply every value by a coefficient, just as if I was writing a mathematical function. That is the function of my line. It is coefficient multiplied by variable plus other coefficient by other variable, etc. And what we want also, so that's going to give the shape of my line, but then this line, how high or low is it on my plot? That's the intercept. So this is what this little factor is there for. Like many things, this is not something you have to worry about. Our libraries will take care of it for you. Now we're going to multiply those values by those weights, add them together. And after that, because if we just do that, we're going to have lots of very, very big numbers. There is a final extra step we do. It is that we're not going to output the raw value from that sum. We're going to pass that sum through an activation function that is going to transform it and generally reduce it, but not necessarily. The activation function is going to transform those raw values into a special space. And different activation functions will have different benefits depending on the kind of network we use. And that's going to be our output. So every time there, what comes out of the blue is not actually the weighted sum of all those greens, it's the weighted sum of all those greens passed as input to the activation function. And what we get there is the output. This is the equivalent of receiving enough information there before we fire out something. The activation function is that. This is the function that is looking at the amount of information received, and based on that, is sending a proportional response. Okay, so the details here. We're not going to look into the details. I'm just going to show you just a few examples there. Yeah. So here there are 3 examples of possible activation functions that you might be using. So in blue, this is the sigmoid function. You remember I showed it to you in the context of logistic regression. So the sigmoid is going to transform any range of data into a value between 0 and 1. So that's pretty neat, because even if I have very high value, very low values, I just rescale everything into 0-1 interval. And the nice thing about that is that neural networks tend to work better if they have values that are close to each other. If a node is giving me values like between 1 and 10 million, and another one is giving me values between 0 and 0.0003, it's going to need to make some drastic adjustments of weights so that those 2 inputs can be compared. So when values are normalized to smaller intervals, this is very nice. And having something like the sigmoid as an activation function is going to help propagate that through the network. Now, another function, for example, in red, I have the step function. This one is pretty drastic. That is, it is either firing. If the value is positive, it will return 1. If it's negative, it will return 0. This is a binary thing. Basically, it's a threshold. If some values are high enough, it will send a signal, otherwise not. So the hypertangent is another one. I don't have it there, but what you see in green, this is an interesting one. It's the ReLU for rectified linear unit. It is going to return 0 if I have a negative value, and if I have a positive value, then it's going to return that value. So if I have 1, it returns 1. I have 3, it returns 3, and so on and so on and so on. This simple function is almost insulting because since the origin of neural networks, mathematicians have looked at the properties of the various activation functions and debated between the sigmoid and the hypertangent and all the possible variants of those fancy functions that are rescaling an input value into another one. And this thing there that is returning 0 for negative values, or otherwise the value itself just happens to work wonders, like magnitudes better than any other function when you have a deep neural network. There are several reasons behind that. I won't get into the details, but just keep in mind that this is the generally default activation function for deep neural nets. It works wonders. It reduces some problems that we have when we're trying to adjust the network. It helps alleviate what we call the vanishing gradient problem, where gradients are so small that it becomes, there's a cascade of effects. That means that some gradients adjust very, very, very slowly. So you would spend tons of time trying to adjust your network. It would be very slow. So this helps alleviate it. And the beauty of that function also is that it costs nothing to a computer, because it's a simple sign test. Is it positive or negative? It's negative, return 0. It's positive, return the value. That's it. No complex calculations compared to the exponentials and divisions that you need to calculate a sigmoid or equivalent. So this function there is absolute magic, and is one of the constants of deep networks. Okay, so I have an example there, but I guess you can trust me on that. Let's say I have two values, two inputs, x1 and x2. I have two weights, 1 and 2, and a bias weight. So my node is going to multiply each input by its current weight, sum all that together. So for my weight, I multiply it by 1. I have all that. It is minus 2.7 is my weighted sum, and I apply my activation function. So here I apply the rectified linear unit. Minus 2.7 is negative, so my output is 0. There we go. My blue node is sending 0 onto the arc. So let's say that this was here. What I send there is a value of 0. And because it's multiplied by the weight there, multiplied by that, well, there's a 0 there. There we go. So these outputs will just disregard whatever comes from here, and will just be a weighted sum of that. So now you know how to interpret a neural net. And if I give you inputs, I give you the schematic, you know that each arrow there is a weight. And I tell you what the activation function is. So you know how to go from the input to the output. You can calculate that, you can program it, and well, any library is able to do that. Now the question is, how do we train that model? Because as I said at the beginning, at the start, well, you don't know what good values to put in there so that the input there results in an output that is close to the one we expect to find from our training set. So this is where we go back to our loss function. If you remember before, we took a loss function, which was calculated based on the difference between the actual outputs and the predicted outputs. So we know what the price for the house one. We pass the first house from our data set. We know the price of that house, but our network with these with the garbage weights there is returning us a very, very wrong price. It is very off. If we calculate the difference between the actual price and the predicted price, this is our error. If we calculate that with more houses, we have more errors, and we can calculate a mean error. This error, the way we calculate it, this is a loss function. This loss function is a function of those all these parameters there. These are all the parameters that we could modify to reduce our loss. If you remember gradient descent, what we do is that we calculate the gradient for one parameter by freezing all the others, disregarding all the others, and just inspecting what happens if we vary one parameter. So here, this weight there, let's freeze all the others, and we calculate the loss function, what the loss function looks like, thanks to the derivative. And we are going to find out, according to the gradient, whether this weight should be increased or decreased in order for the loss to become a little lower. Then we're going to do the same, but for this weight, and for this weight, and for this one, and for this one. And once we have that, what we can do is we can take a look at this weight, and this weight, and this one, and this one, and this one. And basically we can do all of them. And we can go from the output all the way back to the input and test every single weight in our graph and use our loss function to calculate gradients and then adjust those weights. This is the exact same thing as in the ridiculous example we had with a single predictor variable and a single output. It is the exact same thing. We just have more parameters. But this is the magic of that approach. And our mathematical library that was able to calculate those gradients will still be able to do it as long as we have the loss function. So this is how you train a neural network. You define the graph of your network that will determine how many nodes you have, how many layers, how everything is connected, how many weights and biases you have that need to be optimized. And you're going to initialize it with random values. Or you can be a bit smarter. There are specific ways to initialize networks in other ways, but that's irrelevant for today. Just put random values there and it's fine. Then you're going to run what we call a forward step. That is, you're going to pass input into the network, calculate what their predicted output is. This is your forward step. And then you're going to compare that with your loss function. Your loss function is going to use the predicted output and the actual output. This is supervised learning. Your training data contains the known actual output. You're going to calculate your loss. With this loss, you're going to calculate the derivative of your loss function. Well, not you, but your library is going to do that. And it's going to use that to calculate gradients and propose your adjustment for every single weight in the network. This is your backward step. You're going to go from the output back to the input and adjust every single weight a little bit so that we're a bit less wrong. And once that is done, that's it. You have adjusted your network a tiny bit, and it is a tiny bit less wrong. And the bigger your network, the more parameters you have, and the less the reduction in loss. A bigger network will take more steps to actually train. And that's it. There are lots of fine details, but ultimately, this is how these things are trained. And this is the exact same thing as in the trivial example we were looking at. Now, something else to touch on before we get into the difference between these and deep neural networks: multiple outputs. This is something I touched upon before when I was talking about classification problems. I was mentioning using the sigmoid so that we would predict a value between 0 and 1, and that could be used, that could be targeted as the probability of being of class 1. And that worked for binary classification, but if we had 3 classes like green, yellow, and blue, all of a sudden we can't do that anymore. So what do? Well, in a case like that, we have the Softmax function. It is an equivalent of an activation function. And what it's going to do is it's going to take an arbitrary number of inputs, let's say 5 inputs, and it's going to return me a vector of 5 outputs, except the output will have the property of being a probability vector. That is that my 5 outputs will, if I sum them up all together, they will give me 1. And that means that the softmax, which actually is a generalization of the sigmoid, the softmax is transforming raw values into a probability vector. That means that if I have a problem and I want to use a neural network to predict whether a picture is containing a cat, a dog, or a house, I would have 3 output nodes there. 1 for cat, 1 for dog, 1 for house. And I would connect them to a softmax layer that is going to transform those 3 unbounded values because they just come out of the network, and it will connect them into actual probabilistic prediction. So there. Let's have another node and another node. So now I'm connected here, and I'm connected there. And here, I'm going to have these 3 values connected to my softmax. And my softmax will return me a vector of 3 values. And it will tell me, for example, 0.6, 0.3, 0.1. This will be dog. This will be cat. And this will be for house. And this there tells me that I have a 60% chance that this is a dog, 30% chance this is a cat, 10% chance this is a house. This is my result there. Those raw values that are unbounded have been normalized into a probability vector. And the beautiful thing about this is that I can use that for my training to calculate the loss, because if I pass an image that contains a cat, I know that what I would expect for ideal values would be 0, 1, and 0. That's what I would want when I pass an image with a cat. These are the values I would expect the network to return to me if it was perfect. So now I can use those predicted values and those expected values to calculate my loss and to train the network. And the network over time will learn to predict something close to that. So this is when you see softmax, these softmax functions, generally it is that you are dealing with a classification problem and you have more than 2 classes. And the softmax is turning your raw values into probabilities. And that's it for the softmax. So the final bit we have to discuss neural nets is the deep network. So this is probably the main thing that is bringing you here today. It is those deep networks. They are the ones that are doing all the fancy stuff these days. The idea behind them is incredibly simple. If you think of the network topology, the shape of the network, if you remember, we have our inputs, then we have a hidden layer, and then we have an output. Now, if instead of the output, we had another layer, and another layer, and another layer, and another layer, and then the output, we have a lot more connections, a lot more possibilities, a lot more representation. So we can have something a lot more complex. So very, very complex combinations of parameters with nonlinear features due to the activation functions are going to be possible to represent with a network like that. So this is the original idea. It is that, okay, we have those neural networks, they can do stuff with a few layers. What if we added 10, 20, 100 layers? We could do a lot more. This is fine in theory, but in practice, it didn't work. It just wasn't possible. So why wasn't it possible, and why is it possible now? So there are a few reasons for that. Computational technology is a big one. The calculations, especially when you're backtracking the network, calculating the gradients and adjusting them, this is costly computationally. The more layers you have, the more complicated it is. Because I didn't enter into the details, but to calculate the gradient of a weight at the beginning of the graph, it depends. We can calculate it more smartly by using the gradients from all the nodes behind in the graph. So all these calculations depend on each other. So there's a lot of CPU required. And back in the 60s, well, no, that just wasn't possible. So there was a hard limit over what they could do. Plus, even these days, on a CPU, it becomes incredibly complicated. So a big game changer are the discovery that the graphics cards used for gaming are because they are optimized for matrix operations, which are very useful when you do 3D calculations for games. Those graphic cards, they are a particularly good fit for that technology, because all those operations in a neural net are based on matrices, and there are matrix operations that can be parallelized, and the GPUs, graphical processing unit, and GPUs are general purpose graphical processing units. These cards can do that very, very fast, magnitudes, an order of magnitude faster than the CPU. So all of a sudden, we have the technology that allows the computational part. What would have been done, in several months of calculations, we can do that over a few days. Then another one is storage technology. If you remember, I talked about data volumes, and we talked about overfitting. And an issue with overfitting is when you have too complex a model for the amount of data that you have, it's going to be very easy to overfit. So if you have a model with 1 million parameters, you are not going to train it efficiently if you have just 100 data points to train it from. That's not going to work. So you're going to need millions of examples. And these examples, well, you will need them. You will need to store them. You will need to have them available. So back in the days of 20 megabytes hard drives, well, it was just unthinkable to have these data volumes. And in any case, there was another issue, which is the relationship between society and data. It is only now that the data collection craze is omnipresent. Probably since, I don't know, 10, 15 years ago. Before that, we didn't collect as much, but these days, with cheaper storage technology and with the value of data from early AI models being shown, with that value of data being present at the back of the mind of deciders, all of a sudden, we are storing the data because it's cheap and because we know there is value to be had from it. Sorry. Apologies. So that means that now we have those data sets. We have them in-house. We have them personally. We can crawl the web to extract them. Lots of data sets are available. And all of a sudden now, these models have the amount of data they need to be experimented on. And this is how things are moving forward. So typically, the ImageNet data set has millions of images from the web. It is a giant image collection set with annotation that has been built over time for the purpose of training those AI models. And it is a brilliant source of data now, for example. But there is a lot more available. Now, that's the idea. The deep neural network ultimately is just a neural net, just bigger. It will require more data, more processing power, but that's okay. We have all that these days. Now, there are a few extra tricks, and I'm going to talk about some of them now. Deep learning networks will have a few extra bits. They will have a few different type of nodes, a few different layer types that are going to help with the large volumes of data that we're dealing with, and that are going to help us with some specific types of data. So I'm not going to talk about everything. For example, I'm not going to explain how recurrent nodes and LSTMs in particular work. So these are nodes that are not just sending their output to the next layer, but they're also sending their output back to the same layer they are in, but for the next data point. So they're used in time series. They're used for natural language processing. When you have words processed one after the other, there is an order sequence in the data that you want the model to be able to model. So there is some fancy stuff there. I'm not going to talk about all that, but I'm going to present the two big ones for CNNs. What we call CNNs are convolutional neural networks. And they're called like that because they use this preeminent layer, the convolution layer. So what is the convolution layer? Convolution layer is a layer in your neural network that will be based on a small number of parameters. If you remember the neural network schematics, if we have a number of nodes and we want to go to the next layer, so let's say here, I'm going to need a weight there, a weight there, a weight there, a weight there, a weight there. If I have another node here, I'm going to need that many more weights, and so on and so on. So that's a lot of parameters that will need to be optimized. Plus, and the reason for that is that every node there is connected to every single node before. Now, this doesn't necessarily scale well, and this is making it complicated to work, for example, on images. If you think of an images as a grid of pixels, let's say you have 100 pixels by 100 pixels, that's 1,000 pixels. So if you take this as a flat vector, you have 10,000 inputs. And if you want to go to the next layer, if you have even just one prediction with just one node in the next layer, you need 10,000 weights to go there. 20,000 weights if you have two nodes in your next layer. This isn't really great. Plus, you would imagine that on an image, pixels are, what you want to explore is how pixels are connected to each other, to the ones around them. So you want some sort of degree of locality there. So this is what the convolution layer is going to give to us. The parameters of the convolution layers are just a small matrix. That is the convolution kernel. And it's a matrix, and you choose the size of it. So let's say a 3 by 3 matrix. 3 by 3 matrix, that's 9 weights. That's all. And we're going to process all our entire data set using those 9 weights. So this is the layer that will be very economical because there are very few weights to adjust. And the backpropagation gradient adjustment will work on them. These 9 weights will be adjusted over time to reduce the loss, just like anything else. Now, okay, what's the point? How does it work? So I have this little Python example there. So if you get the notebook and if you can deploy it at home, feel free to play with that. So this is, I'm just loading an image. I'm extracting just one of the 3 channels from it, the blue channel apparently. And then I'm generating convolution kernels. So I have an example there. I have another kernel here. So 3 by 3, 3 by 3. And I have a custom kernel, which is just random values there. It doesn't mean anything. And it is a 5 by 5 kernel. So this one has 25 values. And I'm applying the convolution. So what is the convolution? It's pretty simple. If you imagine this convolution kernel, 3 by 3, you can imagine that I'm going to, where is my pen? I have my image there. and my image is composed of pixels. In order to convolve this image, I'm going to take this kernel and I'm going to move it onto my image. So I'm going to start and put it there over those 3 by 3 values. And I'm going to multiply the weights in my kernel by the values of the pixels under it. So 0.1 multiplied by that, plus 0.1 multiplied by this, plus 0.1 multiplied by this, blah, blah, blah. And then I calculate, I calculate my weighted sum, and this is the value, the new value I have for this pixel there. Then I'm going to move my kernel here. I'm going to do the same to calculate the value of that pixel there. And for the next, and so on. And then I'm going to go there. So I have this slide. I'm going to use this kernel, this matrix, as a sliding window over my image. I say image, but ultimately any two-dimensional data set is going to be the same. As long as I just have a matrix, it just happens that an image is represented with numbers. And that's going to give me this transformation, which is called an activation map. And what's the point? The point is that these activation maps, if we choose the correct weight, that activation map is going to be very interesting. So this is my original image. Now this is my image using my first kernel. So can you see the difference there? This one is blurry. This is not very useful, but that's what it does. This is because I'm just calculating the value there by averaging the values of all the pixels that surround it. So obviously, this is going to be a mishmash of the 9 pixels that was surrounding it. So this is a blurred version of the image. Now, more interestingly, this one there is an edge detection that is going to detect vertical edges. Look at that. Now I have very high values, the bright, and very low values, the dark, when there is a vertical line transition, a vertical transition between high and low values. So I am detecting all those vertical lines. You can see that the rest is has more neutral values. This one there is just a garbage filter. I put random values. So this is the kind of thing that you get when you initialize your convolution layer with numbers that are meaningless. But as we've seen before, these are parameters of the model. And these here 25 values, for example, if I was using that, when I calculate the loss of my model, it will realize that the loss is bad. And we'll find ways to adjust all these so that the loss becomes better. And let's say that I'm trying to detect houses on my pictures. In order to detect a house, it is likely that I will have walls. Those walls will be, at the side will have vertical lines. So it will slowly converge to a kernel that will look a little bit like this, except on a 5x5, but it will ultimately be encouraged to converge to a configuration like that, that will detect those walls, that will return high values where there are walls, and those high values are going to combine into a high probability that the image is a house. This is if I have a single convolution kernel in my layer, but a convolution layer can have multiple kernels, and instead of generating a single activation map, you can generate multiple activation maps. That means that you can have multiple filters, and this is generally what you want, because there isn't a single combination of features that will give you what you want. You want some information about vertical lines, you want some information about horizontal lines, about little curves. There's lots of kernels that could extract something interesting. So you might want multiple kernels in a single layer. This is all well and good, but now we have a problem. That is, we have input data, So let's say we have an image which is 10 by 10 by 10 pixels. That is pretty small, but still 100 pixels. We use a convolution kernel. We're going to have an activation map, which is going to be a little smaller. Due to the boundaries, it will be 8 by 8. This is still a lot of pixels. Plus, we'll have double that if we have 2 convolution kernels, triple that if we have 3. So the more kernels we put, and the more we are actually increasing the volume of data that we have. And all of a sudden, we have more data on after the second layer than we had after the first one. And that is not going to scale. We're going to have a computational explosion there. So this is where the pooling layer comes from. And this is why you will often see it and associate it to the convolution layers. The pooling layer is a layer that's used to downsample your data. So it's going to reduce the size of your data so that even though you're expanding it with multiple convolution kernels, you're going to reduce the size of these activation maps so that you don't have this data explosion. So the pooling layer, just like the convolution, is I think you can think of it as a moving window. So here, my pooling layer is 2 by 2. This is something that you can configure. And I'm going to move this 2 by 2 window across my data. Here, I'm moving it by 2. So this is what we call the stride. The stride is by how many columns or rows you move your window every time after operation. And the question is, okay, what value do you take for that? You can take the mean value, you can take plenty of things, you can have multiple strategies, but what you will find very often is what we call max pooling. Max pooling simply consists in taking the highest value that you have in there. So for this, we'll take 20. Then we move our window, our stride is 2, so we move it by 2. Now 18. Then we look at that, the highest is 25. Then we look at that, the highest is 17. There we go. This there is the result of this after max pooling with a 2 by 2 window with a stride of 2. And we have divided the size of the data by 4. So this is a considerable reduction. That means that we could afford 4 convolution kernels before, and the size of our data hasn't changed. Yay. Now, the reason why max pooling is so often used is that if you look at this, this is an example of an activation map. An activation map is a result of a convolution. And activation maps will have high values for the specific features that they highlight. Here, this is a vertical edge detector that is detecting when there is an increase. So those high values are the features I'm interested in. So I will have high values in interesting parts, and the rest, boring parts, low values. We don't care about them. So what the pooling is going to do with max pooling, I'm just going to say that, hey, look, in this top quarter of the image, there is an interesting feature, and this is how interesting it is. That's all we're doing. We're just preserving the information. There is something interesting in that section of the image. This isn't lost. And if we had a bigger data set there, again, if this thing was convolved and then pooled, again, we start from those high values. This is how those interesting features then will be combined together by other convolution kernels. So that's pretty much all the tools you will need to make a CNN by now. So the final bit is to show you an example of a CNN. So this is an example there. This is a famous net called Le Net by Yann Lequin, one of the pioneers of deep learning. And it was used for deciphering handwritten digits, and we'll actually look at an example of that. So this is an input image there. and you have 6 convolution kernels that are going to create 6 activation maps. And then you have a pooling layer that is going to reduce them to 40 by 40. Then there are 16 additional convolution layers, and then another pooling layer that is going to reduce them. And then those 16 5 by 5 matrices, they're going to be what we call flattened. That is, we're going to take all their values and put them back to back as the input of a traditional neural network. And we're going to connect them to a hidden layer of 120 nodes, connected to a hidden layer of 84 nodes, connected to 10 outputs, 1 for each possible digit. And we're going to train that model, and it will work. So this is an example of architecture. And the point of getting your hands a little bit dirty with TensorFlow, with PyTorch, with Keras, with CNTK, is that it will allow you to design models like that. There are state-of-the-art models that you could take and use out of the box, but they might be too complex for your use case. Maybe you don't have enough data to use them, to make use of them, or maybe the transfer learning won't work. So with those frameworks, you will be able to design your own model. And this is what we're going to look at after a small break. So I propose, in the interest of time, let's take 7 minutes. So we meet again at 20 past, and I'll get you around a few examples with Keras to show you how all that stuff is implemented with very, very few lines of code. So I'll see you at 20 past. Thank you. All right, welcome back, everyone. We'll get back on track. I don't want to presume that everybody's working from home today, so in case some of you are need to catch a ride home, I just want to avoid getting too much overtime. So just before I do, I think I mentioned this being used for reading digits. This is a bit silly of me. This is actually this model there, I think was originally designed for the CIFAR 10 image set. So there's an image set with 10 categories of images. Images are 32 by 32 and represent 10 categories. So I think there's ships, airplanes, and I can't remember all the others, but this is typically a data set that you will find inbuilt in all the training sets. And the reason for that is that this is actually a much more complicated case than reading the digit, as we'll see in the session now. So, okay, putting the stuff into practice. So in the first section, first block, I showed you I talked about the basics of those models. So what is a loss function? What is an optimizer? What is the optimization? How we use gradients to adjust the weights of a model? How we can have an arbitrary number of weights and adjust them all just by putting more computational power onto it. Adjust everything so that the loss is a bit reduced, and how that ultimately is helping our model become better, and how we split the data into training and testing so that we can train it on one partition, test it on the other, and make sure that we don't overfit. Now, the question is, okay, how do we put all that into practice? How do we implement it? So I'm going to show you a few examples now using TensorFlow as my framework. TensorFlow and PyTorch are two of the biggest ones. They're the two I would use the most personally. I use some other ones, but they are more fringe, and I wouldn't recommend them unless you like some of the specific features they have. But the TensorFlow and PyTorch would be the two big ones you're most likely to fall into. And the reason I picked TensorFlow for today, for this introduction that I do every now and then, is that TensorFlow has something that comes on top, which is called Keras. Keras is not a standalone framework. It is a high-level API that plugs on top of TensorFlow, and it simplifies a lot of things. So that's going to make, to allow you to design those networks with very, very little code. So a reference there, just a note, a lot of the code below has been picked up from the TensorFlow tutorials, some of it adapted. So have a look there if you're interested in TensorFlow, because there's a lot of information there, a lot of stuff to go through to get started, to get a feel for it. And same for PyTorch, there is plenty of tutorial content in the official documentation. So take a look at it, try to go through it, experiment with the code. This is a great way to learn. So first, quickly, to dispel any kind of vocabulary issue, there's a lot of talk about tensors, and TensorFlow is named on them. When you see tensor, don't be scared. It is nothing mysterious. A tensor is just a multi-dimensional array. That's all there is, really. It is called a tensor in this context, but ultimately that's it. If you think of your 3D matrix, well, that's a tensor. Cool. Well, technically it is a matrix, but you could make a tensor that is exactly identical with the same stuff. So that's all. So a tensor has a number of properties. It has a rank and a shape. This is just something you want to know, because you might end up with error messages that complain that a tensor is of the wrong shape or the wrong rank, etc. So just need to know what that means. The rank of a tensor is the number of dimensions it has, or if you want more simply, how many indices do I need to give you to identify a specific value inside. I'll show you what that means. And the shape is the size of each dimension of the tensor. That is, how many elements are there in each dimension, so the size of them. So I have a few examples there where I use TensorFlow to create constant tensors. So this there, this tensor there is a tensor of rank 1. Funnily enough, it is a tensor of rank 1. It just happens to have a shape of 0 over the first dimension, but it has a dimension. It just happens to be empty. It has 0 elements in there. By comparison, this one there, this is funky because this is a tensor of rank 0. It doesn't have a dimension. It just stores a single value. So I don't need to give you an index to point at this one. There's only one. Here I have a tensor of rank 1. It has a single dimension, and the shape is 3 for that dimension because it has 3 elements. Here I have a tensor of rank 3 because it has 3 dimensions of the shape respectively, 2, 2, and 3. And really, that's about it. Now, in addition, if you use TensorFlow, tensors have something called D-type, and that's the type of data it contains and can be a single type. So for example, this tensor there is valid because it contains only string type content. If I try, so if I execute this cell, that's fine. If I try to do this, to load this tensor there, where I have strings and here an integer, it's going to complain and tell me that I can't code for a living. There we go. Okay, so that's it. Then a few very basic things about TensorFlow and manipulating tensors. You have specific operations around them. So if you want to manipulate them manually, you can do that. You have an operation to add them, square, reduce, do map reduce. There's plenty of stuff in there. Honestly, that's not the topic of today, and it's very unlikely that we will need that. Because ultimately, what matters is this. It is NumPy. If you use Python, and if you do anything serious with numbers, you very likely have used NumPy in the past. It is pretty much part of core Python at this point in time. If you're manipulating arrays, you use NumPy. That's all. And NumPy multidimensional arrays can be directly converted to tensors, and the opposite is true. You can generate a NumPy array from a tensor. So if you need to manipulate your data, do it with NumPy, and then you transform that into tensors. That's it, job done. You don't have to know about TensorFlow. So you have examples there. Feel free to play with them if you get hold of the notebook. Adam has pasted URL to the download point for the notebook with all its data. So feel free to play with that. And finally, one of the main differentiators between a tensor and a NumPy array is that whereas a NumPy array is in your RAM, a tensor can be there, but it can also be actually in the memory of your GPU. So you can play with that, and then you can move tensors back and forth. Generally, it's not something you'll have to worry too much about if you use a high-level API. And that's what we're going to do today. So just for the sake of being thorough, since TensorFlow 2, there is something called Estimators, which is another high-level API for TensorFlow, which allows you to write models without doing everything manually. But I'm not going to touch that today. I'm just going to focus on Keras. Keras is something that used to be standalone, and it could work with either TensorFlow, Theano, or Microsoft CNTK as the backend. So you would write your Keras code, and then everything would be executed using either of the three frameworks. It is still available, but the main thing is that since TensorFlow 2, there is a version of Keras integrated, inbuilt inside TensorFlow. So if you enter TensorFlow, you have a version of Keras in there already. The two are supposed to be fully code compatible. So in theory, the code you write for one will work for the others. So let's do some work with it. Let's get an example. So we're going to use a famous machine learning dataset, which is called MNIST. So you can find it on the web. If you Google MNIST, you will find it. And lots of frameworks like TensorFlow, PyTorch will have that dataset available as an inbuilt function. So you can call a function and it will automatically download it for you and load it up in memory in nice tensor format. So you don't have to worry too much about reading the files. So it is thousands, tens of thousands of images of 28 by 28 pixels, grayscale of handwritten digits. So that's what it looks like. Lots of these. And it is used then to train models and to compare models on how good they are to recognize the handwriting. So I'm going to load it. As I said, it is available inbuilt as part of the inbuilt Keras dataset. So if I load this thing there as MNIST, that's it. It's going to download it and store it as a tensor. I have it. I don't have to worry about it. And that's brilliant. So MNIST is my data object. There's one thing you need to do on the data object is this load data, and then that is what is going to actually perform and convert everything to a tensor. And then the way this load data is going to return me information, and you can find that if you look at the documentation, it's going to return me 4 separate tensors. It's going to return me a tensor for the predictor values, so the pixels of the training set. It's going to return me then the actual values, the value, what digit it is. So so here I will have a number of 28 by 28 matrices. And here I will have as many digits as matrices. Each time the digit, the integer I will have will tell me what is the number represented on the corresponding image. And then I will have the equivalent there, but for the testing set. So this, going back to the question earlier, this is a case where if you use that thing there, or not doing the train test split, it is being done for you. But here, this is not a production case, so we can just trust it for the day, and that's fine. Here, what I'm doing is I am rescaling my data. So these grayscale images, each pixel is encoded with a value between 0 and 255. Here, I'm dividing everything by 255 to have values between 0 and 1. This is a normalization process. This is just to help out the network a little bit. Neural networks like to work with values like that between 0 and 1. Yeah, it just helps them. So that's going to help a bit our training. That's not necessary. It's just a nice touch here. So here, I'm just having a look at it. So don't stress too much about what it's showing there. But just to explore, we'll just use TensorFlow and convert to tensor the X-train, just to see it like that. And this is what we have. This is a tensor of shape 60,028 weight. This is a tensor of rank 3. And what I have is I have 60,000 28 by 28 matrices. So that's 60,000 images. And if I look at my Y train, so here I should have the predictions for those 60,000. And this is what I have. And that makes sense. This is a tensor of rank 1 with 60,000 integers. I can see the values there. So my first 28 by 28 matrix must be 105. So the following one must be a 0. The next one a 4. Okay. Let's just look at one of them just to explore our data visually. So I'm going to take one, the number 42. This is what the matrix looks like. That's the values of the pixels. And that's the label, 7. So it should, this there should be a 7. I'm going to use the matplotlib imshow to convert my matrix automatically into an image. That's a very convenient way to do that. I don't care about the color palette because I'm just interested in the shape. And indeed, that is a 7. Okay, cool. So I have my 60,028 by 28 images. That's going to be the input of my network. Then I have these 60,000 digits, which are the output of my network that I want to predict. This is great. I have everything I need. So I'm going to prepare my network. So what is my network going to look like? Well, I have my input layer there. So how many nodes will I have there? I'm going to connect everything. So I have 28 by 28. That's how many input nodes I'm going to have. And I'm going to connect all of them into a hidden layer with 128 nodes. And then I'm going to connect that to my output. And my output, this is a classification problem. And there are 10 digits that I want to predict. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs. And of course, each output will be connected to each of the 128 nodes from the hidden layer. And that's it. And I will have raw values coming out of that. And if I want to turn them into probabilities, well, what I will use is I will apply, if you remember, my softmax function, which is going to convert those raw values into a nice probability vector. And that's my model there. A simple neural net. It's not particularly deep because this is really an easy problem. So how do we code that with Keras? This is how. 5 lines, and that's because I'm trying to be stylish and I'm putting stuff there on the line there. Otherwise, this is actually a one-liner. So I'm using Keras and I'm coding for a sequential model. A sequential model is what you're pretty much always going to use when you're beginning. It is a model where you have a number of layers that are connected from left to right. And there is no interlinking, no going back, no connections. Your model is flowing from left to right. So this is a sequential model. And inside my sequential model, I define what layers are in order from left to right. So my first layer is going to be my input layer. My input layer, is going to be what is connected to my input. So my input is 28, if you remember, 28 by 28 matrices. That's what I'm going to receive as input. I'm going to take that. This is my input shape, 28 by 28. And what I'm going to do is I'm going to push that into a flattening layer. Flattening layer means that I'm going to put all my pixels back to back as a single flat vector. So I will have a 28 by 28 flat vector with all my values. That's my first layer. So I have my matrix there, 28 by 28, and it's going to go to the flattening layer. So it's going to become just a big long vector with the same number of elements. Then the next layer will be a dense layer of 128. That means that this is the layer where I have 128 nodes, each one connected to every single value from the layer before. And each line that I'm drawing now is going to be a weight in my model. And finally, my third layer is going to be a dense layer with 10 elements. Dense layer is just, a layer of nodes like that with everything connected to the previous one. So here I have 10. And because this is a sequential model, everything there is just connected to the line before. And that's it. That's my model. And I can work on it. I can train it. Or can I? Well, we'll see. Now, our model is defined. We can look at it. This summary command will allow you to inspect a model that you have defined. So if I look at it out of curiosity, you have this thing there. The nice thing about it is that it shows you every layer, the shape of the output that it produces, how many parameters and what shape. And it shows you also how many parameters you have in each layer that you're going to optimize. So you can see that there, this network I designed there has over 100,000 parameters that it will need to optimize. And this is the beauty of computers these days, that this is a super simple problem and that will take no time at all. So now I can apply my model. I can try to use my model to predict. So I do model, I pass it a tensor of the proper shape, and I get a prediction. So my prediction is going to be a vector of 10 values because that's the shape of my outputs. So I have 10 values there, some high, some low. And of course, it's not between 0 and 1 because I didn't apply a softmax. So that's raw values. And if I apply my softmax now, there, I have a nice probability vector. It tells me that my value is 0, 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 6. So it's predicting the 6. But of course, it doesn't mean anything because my model has been initialized with random weights. It hasn't been trained yet. So this is probably just the randomness of the prediction. So what do we need to train the model? Remember, we need two things. We need to define a loss function so that the model knows how to calculate the error. And we need to specify an optimizer, an optimizing strategy so that it knows how to use that loss function to adjust the weights. So that's the two things we need to define. Loss functions, there is a category of objects in Keras which contain loss functions. So if you look at the documentation for these, you will have all the inbuilt loss functions there. You also can make your own, but you shouldn't need to for a farewell, if ever. This is one of them. So this is those cross entropy, categorical cross entropy. They are families of functions that work for classification problems. You remember the mean square error, for example, is something that works for regression problems. If we are looking at classification, we need a different kind of loss. Remember that I was comparing to probabilities and calculating probability vectors that we expect that we should have a 1 if it's class 1, we should have 0 if it's class 2. So this is what this loss function is going to do. Is going to do that for us. All we have to do is just match our predictions. So I'm just defining that. And it is even fancier because this sparse categorical function is going to take the values, because if you remember my y values, what I have, I don't have a vector of 10 elements. I just have the number of the digit that is predicted, 7. So this is a digit 7. In theory, what I would want is not 7, but I would want a vector like that with 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the vector I would want, because that's what I want as output from my network. I want a 0 everywhere except on 7th node where I would want a 1. But what I have in my data is just the number of the one that is the correct one. Well, the sparse categorical entropy function is smart enough to do that for us. This is one of the wonders of using those tools these days. So you don't even have to transform your output. The loss function does that for you. So I can test my loss manually, but I'm not going to do all that manually. I'm going to compile my model and prepare it. So I'm going to compile my model by specifying which kind of optimizer I want. So Adam is a classic state-of-the-art optimizer. Stochastic gradient descent is another one. So you have lots of strategies. Adam is a very, very good one. It's a classic one these days. I specify my loss function. I already have chosen it above. And I'm going to specify what metrics I want to see while it's training. This is optional. If I'm not interested, I don't put anything, that's fine. Here, I just want to see the accuracy as it goes because it's more visual. And that's it. So ultimately, this, that, and that has been enough to define my model. And now I can train it. I can train it with the fit method. So model.fit, and I pass it my input training data, my output training data, and the number of epochs I want. The number of epochs is how many times I want to go through the whole data set. So I want to go 5 times through the whole data set and have the model train. And if you launch that, I'm not going to do it here because it's going to kill my notebook and my CPU. And it's going to train over the 60,000 samples every time. It will tell you what is the loss, what is the accuracy, and you can see that the accuracy, even after 1 epoch, is already 92% accurate at predicting the digits. And after 5 epochs, 98.6% accurate in predicting it. This is how simple of a use case it is for a neural net. And if we evaluate the training set, if we finally evaluate the model manually over the testing set, and we have accuracy there over the testing set. And it does reflect what we observe there. So we're not in an overfitting scenario. And if I use it, if I calculate the prediction on the number 7 that we looked at before, that was the number 42, the 7th value should be the biggest one. So that's for 0, 1, 2, 3, 4, 5, 6, 7. So this is 0.981 after the softmax. So the probability that this handwritten 7 is a 7, according to my network, is over 98%. That works. So this is an example of a neural network. The only difference, the only thing you would need to adapt that to your own data is to change the input shape, because your data might not be 28 by 28. You might want to change the output shape. If you have another number of classes than 10, you might want to change that. If you are doing a regression problem and you're trying to calculate an output value, maybe you have a single output value there. But ultimately, you can just reuse that code. There's very little. So less than a dozen lines to actually define and train the model. And now, before we leave, I have another example there, sorting out images of cats and dogs. So it's not a great model because the point is not to make it work well. I would need to train it a lot more for it to work. The main point about it is that here, and if you download the notebook and you try it out, what I want to introduce there is these data generators. So those data generators, they are functions that you have available in Keras, and you have the same in PyTorch, to which you tell where your data resides and how the data should be loaded at every step of your network. That allows you to have a program that is not going to need to load all the data in memory and then pass it to the network, but it will only load the batch it needs one at a time, pass it to the network, and then load the next, and then load the next, etc. And you can inject some intelligence in the workflow. And the nice thing here about, in particular, those image generators in Keras is that they come with this flow from directory function. That means that you can create generators that are going to tap directly into folders on your drive. So this is a very simple way to make an image classifier. If you have your images stored in folders and each folder is named after the class, that's it. This is all you need to load your data. You don't need to do anything fancy about transforming the images, loading tensors. All of that is done by Keras. So let's have a look at what it looks like. I'm not going to enter into the details of the code, but the first thing I do is I'm creating my training data generator. So my training data generator, it's going to be an image data generator. And I'm going to define a number of operations there. What I'm doing here is I'm doing operations on those images. So when an image is loaded, it's going to be rescaled by 255. Again, it's to put the values between 0 and 1. Then I'm going to do three things there, which are called data augmentation. I am going to randomly modify the data whenever it's loaded. So whenever an image is loaded for the training set, I'm going to randomly share it with a factor between 0 and 0.2. I'm going to zoom into it with a factor between 0 and 0.2. And I will have a 50% chance of flipping it horizontally. This is data augmentation. This means that every time I'm going through an image, it has a chance to be a little different. So that means that I'm going to artificially increase the amount of different images that my network will see. It will never see twice the exact same image. Every time it will be a little bit different. Okay, and then I'm going to define my test data generator. My testing data generator, however, will only have the rescaling. I want to rescale the data so that the values match the ones used in the training, so that the values are in scale with my network. However, because this is going to be used just for testing, I don't want to modify randomly. I want to pass the image as is and see what the prediction is, and I know what it should be. And these data generators are there. I have them. And now all I need to do is to tell my data generator, okay, where is the content and how much of it should we load every time we are called. So I create my training set and my testing set like that from the data generators. So my training set is created from the training data gen. And I use this flow from directory by telling it, okay, just look in that folder. Each file is a data point. So I point at this folder there, data cat dog training set, which contains two folders, one called cat, one called dog. And same thing for the testing set. I'm pointing to the test set folder, which contains one folder called cat, one folder called dog. Each one has its own images. And I say what size the images should be rescaled. So no matter the size of the image, I'm going to transform it to 64 by 64. So this will be the size of the input in my network. I'm defining a batch size. So I'm saying that every time I want to pass 32 images at a time into the network, calculate the loss for those 32 images before adjusting my weights. And then what is the class mode? Because I just have two classes, cats and dogs. I just want a binary classifier. And this is it. If I execute this, you can see there that Keras is telling me how many images it found for my training set, 4,676 belonging to two classes, and something for the testing set. Now we're defining the model. Just like before, it's a sequential model. The only difference to before is that this time we use the two new layer types we talked about, convolution and max pooling. So my convolution there, I said I want 20 convolution kernels of size 5 by 5. So I will have 20 kernels. I'm going to, for each image, I'm going to generate 20 activation maps with 5 by 5 kernels. This is my input shape, 64 by 64, the size of my images. 3 is the channels, red, green, blue. And activation is the ReLU function, rectified linear unit we talked about. Then I'm going to do max pooling to reduce the size of my activation maps. I'm going to throw another convolution layer, this time 32 kernels, 3 by 3, same activation, a pooling layer. Then I'm going to flatten all that together and just generate a very long vector with all those values and connect them all together into a hidden layer, a dense layer of 128 nodes for the ReLU activation. And at the end of it, I'm going to have a layer with a single node with a sigmoid activation so that I have a value between 0 and 1 because it's a binary problem. So it's either a cat or a dog. And that's it. I compile my model. Like before, I just need to specify an optimizer, a loss function, and the metrics I want to see. For out of curiosity, I'm putting the summary here. You can see that I have over 800,000 parameters to optimize. That is a lot. And in fact, I don't have images here. This is too complex a model for the number of images I have. But there's the break. And I'm going to fit that model. So just like before, I call my model, I do .fit, and then I pass it the training set. I'm specifying how many steps I want per epoch. This is something I have to do there because I'm using data generators. So I don't have, the model doesn't know exactly how many data points it has in each set. Plus I'm doing data augmentation, which means that I would go 2 or 3 times through the entire data and it would be never the same image twice. So I have to specify how many samples, how many training steps constitute one epoch and the number of epochs I want and so on. And that's it. My model is training. You can see the loss, accuracy, and the validation loss. And at the end of the day, validation accuracy is 62%, which is not great, but you can take it as an exercise to modify the network and train it for longer and see how it goes. So I just have this little function there to test the predictions, and this is our partying test. So this, according to my model, is a lovely puppy. Okay, that's not great. These ones are dogs. This one is a cat, and this one is a dog. So we got 3 out of 4. That's better than our validation statistics, but of course we looked just at a small sample. So the model is not great, but it's doing better than the 50-50 random chance. So this is it. You have an example there showing you how to use your data directly from the disk. So if you're looking at your pictures of a product at the end of the production line, there you can very easily put pictures of the fine product or the faulty models or a special situation where something has happened that you want to detect, and you can train your classifier there. And then from new images, you can use your model live to detect when there is an issue. And that's going to be it for today. So I just have 1 minute left. So this will be our parting moment. So last thing is thank you for attending today. I hope that was useful. Don't worry too much about remembering everything I said today. All I hope that you take from that is the general idea around what is loss, how the loss function is used by the optimizer to and to adjust the weights, and just so that you know when you use Keras or PyTorch or TensorFlow, when it asks you for an optimizer, you know what it is. When it asks you for a loss function, you know what it is, and you can look at the documentation and look at the various loss functions and see how to what kind of runs they apply, and you can choose one and be informed about it. And keep in mind the overfitting, and try to keep the number of parameters in check compared to the data volume that you're using. And that's going to be it for me. So thank you very much. And I'm still around for any questions or comments.
Thanks, Bruno. Does anyone have any questions?
Oh, thanks for the kind comments in the chat.
Yeah, I suppose time is tight, Bruno.
Yeah, feel free to contact us if you forget the link to the content. We can send it again. You know, it's not an issue.
So what we're going to do is we're going to have a session next Thursday at the same time, 2 o'clock, Thursday the 29th. So for those of you on the call who'd like to participate in that, just reach out to me. If you don't have my email address, just reach out to me, john.shaw@datavaluehub.com, okay? And I'll make sure you get an invitation to the session next Thursday. So we won't be using Eventbrite. We'll do it using you know, Outlook calendaring and a Zoom call through that medium. So really want to thank you, Bruno. Thanks again for a wonderful and insightful lecture. Hopefully everybody got out of it what you expected, and we'll conclude now. So thank you very much. Take care, everybody.
Thank you.
Thanks very much. Bye-bye.
Bye-bye.